Okay.
So our next speaker is Jose Siqueira. I hope I'm pronouncing you right, from Cambridge.
Jose,
Some
yes.
nice tripos theory and non-standard analysis, a favorite topic of Eric's. So.
Thank you very much for this. I'm actually quite excited to be talking on this topic because it's actually the topic of my PhD thesis. So what I plan to do is, well, I will give a brief recap on how internal set theory works, which is a very nice syntactic approach to non-standard analysis, and say a few things about the technology I'm going to use, which is tripos theory. And then once I've done that, I will try to convince you that you can see the axioms of internal set theory as being the result of the relationship between certain triposes. And finally, try to go in the direction of taking some categories and building some triposes that satisfy those properties. So the overall idea at first was that you have a set theory meant to capture non-standard analysis. And topuses are great to deal with set theories. So maybe there is a topos out there whose internal language happens to be internal set theory. And that was roughly the starting point. But the other consideration is that if you look at the axioms of internal set theory, instead of doing it the usual way, which I'll recap. So you start with ZF set theory, and you add a new unary predicate that we'll call standard. So this is meant to be interpreted as saying a set is standard. And then you give a meaning to this by adding three schemata of axioms. So the first one, the most famous one, is of course the scheme of transfer, saying if you have
Lasse Svensson.
Sorry?
Men visade.
Yes.
So if I have an internal formula, meaning just the formula of ZF, it doesn't use the new predicate, and it happens to have standard parameters, then to show that the formula is true of all sets, it's enough to show that it's true of the standard sets. We also have the scheme of standardization. So if I have any formula, so now it can be a formula that involves the new predicate, so it's called an external formula. And I take a standard set, then in fact there is a unique standard subset of it whose standard elements are precisely the ones of the original set that satisfy the formula. So this is the next best thing to having an axiom of separation for external formula. And you have idealization, which says if you have an internal relation and you take a finite standard list and you happen to have a set such that everything in this list is related to that set, then that's the same as showing that there is a set such that every standard set is related to it. So you can look at this and say you have this new standard predicate, and it has this behavior given by this. But another way of looking at this is to say you have two new quantifiers. Let's call them exist standard and for all standard. And you have axioms telling you how these quantifiers behave. And if you go with that point of view, then it's actually quite natural to just work with the quantifiers directly. And for that, it is quite handy to use triposes. So a tripos on a category with finite products is a first order hyperdoctrine with a generic. Okay, so if you have a tripos, you have these functors from predicates on B to predicates on A that preserve the Heighton implication. And they have both a left and a right adjoint satisfying the Beck-Chevalley conditions. And moreover, you have a generic predicate So there is a predicate lying there somewhere, such that if you have any other predicate, you have a map from A to wherever this predicate lives on, such that your thing is isomorphic in the preorder to the substitution of the generic predicate with that map. I should mention that here, it is actually quite important to have this not take values in Heyting algebras, but rather pre-Heyting algebras or Heyting pre-algebras. We have situations in which, for example, the order we'll put here will be a pre-order indicating things have inclusions up to standard elements only, and you could perfectly have two sets with the same standard elements that are not the same if the sets are not standard. So it's actually quite important to work with pre-orders instead. And the good thing about working with a tripos is that you can think of a tripos as a topos in a box. So if you want to focus on the logical aspects of the topos, this is a good thing because every tripos induces a topos through what's called a tripos to topos construction. And conversely, every topos has a canonical tripos, which is the tripos whose predicates are just the subobjects of something, as usual. Right, so now that we have this background set, the idea is that if we have a model of internal set theory, there are three triposes that you can build over the category of standard sets and maps. So you have the tripos of standard subobjects, the tripos of internal subobjects, and just the tripos of subobjects, which are pre-ordered by the standard elements order. So a subset is less than or equal to another with disordering if the second one has all the standard elements of the first one, but you don't say anything about anything else. Also, I should say that the third tripos, I'm calling it subobjects of something, but this would be, in a sense, the external subobjects. So they're not quite subobjects, they're actually just the actual syntactic external formulae with the pre-order of deducibility up to standard elements. But I think it's not damaging to think of them morally as some kind of external subsets. So the idea is that the axioms of internal set theory can now be formulated in terms of some relationships between these three triposes. So let's start with standardization. Suppose you have a model of ZF and you add that as standard predicate. Then the following two things are equivalent. So first, if you have a standard set, so just a set that happens to be colored standard, and you have a functor from subsets of A to standard subsets of A that is both a left and a right adjoint to the inclusion of triposes, then U is a model for the scheme of standardization and vice versa. And the proof of this is actually quite simple. It's really just noticing it's there and following the definitions. So of course, if you have standardization, this left and right adjoint is given by just taking the unique standard subset you get out of a formula. In this case, the formula is saying something is in the external subset, or the defining formula of the external subset. And you just check that it's a left and right adjoint with respect to the standard elements order. It's quite simple. And conversely, if you have a left and a right adjoint to this inclusion, then just using the definition of adjunctions, you get this. And if you, in particular, apply on your adjunction, taking the the standardization of a formula itself, that's a standard set, you end up finding that the standardization of the formula happens to be a witness to the truth of the axiom of standardization. So standardization is actually quite simple. It's just saying that a certain inclusion has a left and a right adjoint and they coincide. For idealization, the situation is a bit different. I don't actually have a nice, neat characterization of idealization saying idealization holds if and only if this kind of thing happens. But there are still a few things that can be said. So first is that in the presence of transfer, idealization can be used to prove a non-triviality statement. So just saying your triposes of standard subsets and just all subsets will only coincide if you take a finite standard set, which is some sort of, in this setting, related to the usual use of idealization of showing that a infinite standard set has to have a non-standard element. So in one direction, it is essentially this argument. So you take this specific internal relation saying that two elements are related if they're different and in A. And you apply the axiom of idealization to conclude that a set is infinite if and only if it has a non-standard elements. And since you're assuming A is standard, so is the power set of A by the uniqueness principle. So this uniqueness principle is just, if you apply the contrapositive of transfer, it means if there is a set satisfying something, then an internal formula with standard parameters, then there is in fact a standard set doing that. So if that set happens to be unique, it has to be standard. So because of that, you can conclude the power set of a standard set is standard. So combining these things, you end up with the fact that your set is finite if and only if the inclusion of standard subsets into subsets is an equivalence. And in the other direction, suppose you have an equivalence between sub A and standard sub A with A infinite, then using the fact that equivalences preserve top sub-objects, you conclude that no proper subset of A can include all of its standard elements. So that would be the idea. And then you try to get to a contradiction by building a proper subset of A that has all of its standard elements by using the axiom of idealization. So you do this by considering this relation. So you say X and Y are related with parameter A. If they're subsets of A that are with Y proper and Y containing X, which is a singleton. And then you use idealization to show that there is some Y such that for all standard X, X is related to Y in this way. So the idea is that by the axiom of standardization, idealization, you can actually check something like this for finite lists instead, in which case, again, using idealization to argue that if A is a standard singleton, A is a standard, you can just use the axiom of union to build such a proper subset. So the idea is to use idealization to go from this to finite lists and then prove this statement and get a contradiction. So, okay, idealization gives you some non-degeneracy property. And now transfer. So the first thing to note is if you have a model of IST, then the subcategory of standard sets and maps is actually an elementary topos. and the inclusion preserves finite limits and subobject classifiers. And this actually is just, again, from the uniqueness principle. So the idea is that if you look at, say, an equalizer of a pair of standard maps, or a product of a finite family of standard objects, then you can make a choice of a limit for all those diagrams, which can actually be expressed by an internal formula with standard parameters, namely your standard sets. And so by making this choice, you have this uniquely defined limit given by an internal formula with standard parameters, and therefore by uniqueness, it has to be standard. The same goes for power sets of standard sets as before. And since the membership relations are internal, and if they're membership relations on standard sets, they also have standard parameters, the maps expressing the universal properties of the power sets will also be standard since they're unique. So the category also has power objects, so it has finite limits and power objects, hence is an elementary topos. Now, the idea is that transfer will correspond to you having some sort of open map of triposes. So first, we define this map delta A from internal subsets of A into external subsets of A, which takes up some internal subset to the formula. So the external subset given by the formula saying that something is in A and it's in the standardization of X. And if you take that, then we can prove the following. So suppose you have a model of ZF that also satisfies standardization and idealization. Then the standard sets form a topos, and the following diagrams commute. Here, these quantifiers are the quantifiers of the triposes I mentioned before with the standard elements of order. So this diagram pseudo-commute for each morphism that is standard, precisely when U is a model for the scheme of bounded transfer. So this is transfer for formulae bounded by some external set, some standard set, sorry. So one direction is roughly just using the lemma from before to say standard sets is a topos if you have transfer. And the fact that these diagrams commute is really just chasing around the definitions of the quantifiers and the standard elements order. The other direction, the core idea is that if you have a formula that is meant to be transferable, so it's an internal formula with standard parameters, then being internal and having standard parameters means that you can actually interpret this formula in the internal language of the topos of standard sets. So that means if you look at a subset given by this formula, its characteristic morphism is actually a standard map. So you use it together with idealization. So idealization is there to show that the truth value false is actually standard in the subobject classifier. You can use those things together with the diagram for universal quantification to show that you have transfer. So that is the rough idea. Okay, so now let's try to see how we could go from this picture where transfer and standardization correspond to certain properties of triposes to actually building some triposes that relate to each other in this way. So let's start with taking phi to be a Heyting functor between toposes. So it preserves first order logic. And consider this map delta A that goes from phi of omega to the A to omega of phi of A for each A. So I'm calling this the externalization map. So we define a sub-object of phi of A to be internal if the name of its characteristic morphism factors through externalization. And we'll call something standard if it's in the image of phi. So the rough picture is that E is some sort of standard universe, which at least logically sits within this external universe F. And we have this map preserving first-order logic between the standard world and the external world. And you have internal things, which are the global elements of the image of the power object, the standard power object. And of course, every standard subset is internal. So now we can build a chain of Heyting pre-algebras indexed by the topos of standard objects. So we have standard subobjects of phi of A. So the subobjects of phi of A that are of the form phi of S, or some S, a subobject of A in E. We have the internal one, so global elements of phi of omega to the A. And we have the subobjects of phi of A in the external universe. And you can pre-order all of these by the standard elements order again, which in this case is just saying whenever some phi of X is in X, then phi of X is in Y, where X is something in, it's an element of A in the standard universe. And here I say is in, of course, with respect to their notions of membership. So for example, in subobjects of phi of A in F, of course, it's the membership relation of the topos F. For standard subobjects, it's the image of the membership relation under phi. And sorry, that's for internal. And for the standard subobjects, it's essentially with the membership in E. I should also mention that the membership relation for internal subobjects can actually be expressed as a pullback of the membership relation, the external membership relation on phi of A and the externalization map. Now, interesting thing, if your phi happens to be the inverse image of a geometric morphism, then it models the schema of standardization. So the sketch is, if you look at the post sets given by subobjects of A and subobjects of F upper star of A with the usual order, then that map, which just takes a subobject to its image under F upper star, which preserves monos, that actually has a right adjoint as a map of post sets, which takes the subobject of F upper star of A and pulls it back, pulls back the direct image of that along the unit of the adjunction. And then if you just look at the comonad of this adjunction of post sets, then it actually is both a left and a right adjoint to the inclusion of preorders from the standard subsets of phi of A into the subsets of phi of A, this time with the standard elements order. So since we argued that standardization is precisely the same as saying that such an inclusion has both a left and a right adjoint and they coincide, I'm saying that F upper star models standardization. And an interesting thing is that this implies that F upper star of truth is actually a generic predicate for the tripos of internal subobjects. If you look at the condition for being a generic predicate, the map from A into omega that is meant to be substituted with F upper star of true to give you an internal subobject N is the classifying map of the standardization of N. things just work nicely if you have the standard elements order. So, of course, standard subobjects of phi of A and subobjects of I of A both get some tripos structure from the canonical triposes of E and F. And then you might wonder if internal subobjects also can also be upgraded to a tripos. So of course, you have some substitution map, which is just for each alpha, you take phi of omega to the alpha. So in fact, existential quantification along standard maps preserve internal subobjects. And you might wonder if you can change these quantifiers so that you get a left adjoint for phi of omega to the alpha with the standard elements order. In general, I'm not entirely sure how this goes, but I believe it works for open geometric morphisms induced by an open map of locales. And of course, you have a similar diagram for universal quantification. So if you could do that, in fact, you should get a morphism of triposes from the fact that you have these diagrams. I'll just conclude quickly by mentioning how the picture looks like in a localic model. So for familiarity, let's say I have an open continuous map of spaces from X to Y and take a sheaf A over Y. So given what was discussed, sheaves over Y can be seen as a universe of sheaves over X that are standard. So how does this work? So a standard subsheaf of f up a star of A is a subsheaf whose sections are locally given by some subsheaf S of A, but only on top of the image of F. It doesn't know what happens outside of image of F. And a standard element is a element of f of a star of A that's locally given by some coherent sections of A over the image. And being internal means that the subsheaf is locally given by some coherent family of subsheafs of A. So there is no single subsheaf of A necessarily that gives you your internal subsheaf, but in a sense, your internal subsheaf still only comes from morally formulae in the standard universe. So what's happening is that for each open set U, you can find an open cover of U, and on top of each covering set, you have a subsheaf of A that gives you the data of your internal subsheaf, and those satisfy some kind of coherence properties. I should also mention that in case your geometric morphism is an open geometric surjection, so for example, if you take your open continuous map of spaces should be a covering space, then the picture is actually extra nice. So first, f up a star being faithful, of course, means that if you have two standard elements that are equal in f up a star of A, then in fact, they come from the same element in the standard universe, which is something you would expect. But also, the fact that the naturality squares for the unit of the inverse image, direct image, adjunction, or pullbacks, we also get that the standardization comonad that I mentioned before fixes the standard subobjects, which is what you would expect. You would expect the standardization of a standard set should be itself, and that does happen for open geometric surjections. So I guess I'll leave it at that. Thank you very much for your attention in the morning, and sorry about all the technical issues. Hope we didn't go too long over time.
Thank you very much. And
Yeah. So, are you aware of this fairly old work of Koch and Michelson from the 70s, I'm afraid, yeah, who also tried to do a similar thing like a categorical approach to non-standard analysis? That's one question. And the second one, I mean, please don't take it overly seriously. I mean, but what you're doing reminds me of the following. There is a question when you do set category theory, then there is a way, if you have a category C, then people consider the category of families of C indexed over set. Now, this writing of boldface set as that category of sets is a bit suspicious from the point of view of a traditional logician. So, but the question is, how would you do category theory over such a model of non-standard analysis? Thanks.
Thank you. With respect to the first question, yes, the Koch-Michelson paper was in fact the basis for this work. That was the starting point.
Mm-hmm.
Part of it has to do with an attempt to perhaps deal with some issues arising from that paper. So starting with the fact that over there, it's assumed that you preserve your heighting functor preserves sub-object classifiers. So that was one thing that I tried to remedy. But other than that, there is perhaps something about the proof in that paper that is not entirely clear as well, that I was also trying to clarify a bit. But yes, that was essentially the starting point, and trying to use the technology of triposes to perhaps do that in maybe a slightly cleaner way. With regards to the second question, yes, of course, I glossed over quite a bit of details on, say, some underpinnings of what happens when you consider those categories as models of things and so on, which definitely something that will take a lot more attention in writing, so to speak. But there's a lot to be said about what are the foundations you're starting with, and does, say, the category of sets for a model of IST form a topos still this kind of situation. But normally the properties you need for that are all internal, which is why you should, in fact, still have that, since you still have the axioms of ZF going on.
I think Paul Taylor has his hand raised for the next question.
Well, it's a footnote to the previous question. So I'm not sure from Thomas Stryker's question whether by Koch-Michelson paper we mean synthetic differential geometry, and whatever the answer is to that, you'll be asked what's the comparison between your work and synthetic differential geometry. I wonder whether you already have ideas on that, and if not, maybe you think about it later on.
I haven't quite thought about how, for example, models of SDG would fit into this, if at all. But it's certainly something that I had in mind to do at some point, but I haven't quite looked at that yet. But yes, I agree it would be a good thing to do.
Any other questions?
Well, okay. Can I go on? I mean, I never really studied non-standard analysis because I'm a categorist and it wasn't really my thing. So you may encourage me to do so now. So in terms of development of calculus and so on in non-standard analysis, do you have your own take on those things?
To be fair,
In other words,
the
applications.
I mean, I'm not particularly involved in, say, the more practical aspects of the subject, but there are some uses of, say, reasonably low-tech versions of non-standard analysis to prove certain factors in, say, functional analysis and things of the sort. In fact, I think there is actually a quite interesting blog post by Terence Tao on what he calls cheap non-standard analysis. So the bare minimum you need out of some weak model of non-standard analysis to prove certain results. But to be fair, it's not what I've been concentrating on, because I'd be more interested in building models or consistency of it rather than the applications. But they're out there, they exist. That's what I can say.